Okay, we're going to look at some optimization problems. So we've got some word problems here. And the key thing with these kinds of word problems is that we're going to want to maximize or minimize some kind of quantity. So that's why they're called optimization problems. All right, so the first important thing to do when you have these problems is to read the whole problem. A rancher has 200 feet of fencing with which to enclose 2 adjacent rectangular corrals of the same dimensions. Helpfully, we have a figure here on this one. What dimension should be used so that the enclosed area will be at a maximum? All right, so that maximum is what points out that we're doing an optimization problem here as opposed to one of the other kinds of word problems that we've been doing. All right, so read the problem. If needed, draw a picture. We have a picture here, although I'm going to draw a slightly different version of this picture with maybe a few more labels just to make sure we're clear about how all this is working. So we've got the picture here of the 2 adjacent corrals. We see that across the 2 sides here we have X and X. We can't really see any labels that might be on the back of that corral, so those would also be X and X. And then we see up the side that it's Y. But when you draw the picture like this, you might notice that there are really 3 fences that would be Y units long. All right, so, and my picture isn't very good here. It's maybe better in the picture that we were provided where the 2 corrals are the same size here. Okay, so we've read the problem. We had a picture. We made another little picture here with just a few more labels on it. We want to look for the objective function. We want to think about what it is they want us to maximize or minimize and write an equation for that. All right, so the last part here says what dimension should be used so that the enclosed area will be at a maximum. So for this problem, our objective function is going to be area. Our objective function is going to have to do with area. So I'm going to write A equals, and then we need to think about the area of this. So there's a couple different ways you might think about the area of this region. Here's how I would think about it. I've got one fenced region here that is X by Y. So the area of that part would be xy. And then I have another region that is also x by y. So the area of that would also be xy. So my area function here is 2xy. So that's my objective function. You could think about that a little bit differently, but you should arrive at a similar function here for your objective function. All right, the next thing you want to look for in these problems is a constraint. So a constraint is a restriction on the variables here. In this problem, our constraint is that we have only 200 feet of fencing. So we want an equation for that. All right, so we have 200 feet of fencing to fence all of these sides here. So 200 feet total to build all of these pieces here. So if we think about that, we've got 4 sides of length x and 3 sides of length y that we're going to have to build out of that 200 feet of fencing. So there's our constraint. 200 equals 4x plus 3y. All right, the next main step in all of these problems is to use your constraint to reduce the number of variables in the objective function. We have 2 input variables in our objective function here. So we would like to use this constraint to reduce the number of variables in this objective function. So I want to solve this constraint for either x or y. Either way works. I'm going to solve it for x this time, and maybe we'll do another problem where we solve it for y. All right, so if I solve this constraint for x, I'll subtract 3y from both sides. So I'll have 200 minus 3y equals 4x, and then divide through by 4. So it looks like we'll have 50 minus 3/4 y is x. Okay, we're going to take that then and substitute into our objective function. The goal here is to make our objective function have only 1 input variable until you're ready for multivariable calculus where you can handle multiple input variables. But for right now, 1. All right, so we're going to put this in for x. So we'll have 2y times what we're putting in for x here. Oh, I reduced this fraction wrong, didn't I? 200 divided by 4 is not 500, it's 50. There we go. So 50 minus 3/4 y. All right, and I might want to go ahead and simplify that. I'm going to rewrite that objective function, distribute my 2y through to simplify that. So the objective function I'll be using really for the rest of the problem is a equals 100y minus, and then when I distribute the 2y through, I'll have 2 times negative 3/4 will be negative 3/2 and y squared. All right, so there's our objective function that we'll be using. All right, next main step to think about is the feasible domain. So I want to think about what's reasonable in terms of my variables here. We had 2 variables at the beginning of the problem, x and y, but really I'm going to be working for the rest of the problem with this a as a function of y. So when I think about the feasible domain, I want to think about what y could be, minimum and maximum value for y that makes sense in the context of this problem. Okay, so going over here, certainly if y is 0, then I don't have a fenced region. So as part of our feasible domain here, y has to be greater than 0. And then we might think about if there's some highest value that would make sense for y to possibly be. And one way to think about that in this problem is to think about the constraint. If I make y really big, then I don't have any fence left over to make the x sides of this rectangle. So if x were 0, I wouldn't actually have any region here, but if x were 0, then y would be 200/3. I don't want x to be 0, so I want y to actually be less than 200/3, using my constraint to think about my feasible domain here. Okay, so we have our objective function. We know y values that make sense in this problem. We're ready to actually get to the calculus part of the problem. The rest was kind of just set up here. So max-min problems, we want to find critical points and then classify those critical points as locations of maxima or minima, or maybe neither. All right, so this is the calculus part. We're going to find our critical points. So that comes from a derivative where the derivative is 0 or does not exist. So we'll have a prime, and I'm just differentiating this function here. So 100 minus 3y. Pretty straightforward derivative. That derivative doesn't ever not exist, so I can think about when that derivative is 0 and solve for y. So I'll get y equals 100/3. All right, so that is my critical point. I now need to classify that critical point and determine whether I have a minimum or a maximum value at that critical point, or possibly neither. So we've looked at 3 different ways to test for extreme values. We did some problems where we were looking at absolute extrema of a function on a closed and bounded interval. For those problems, we tested by plugging endpoints of an interval and critical points into the function, and we just look for the highest and lowest function outputs for our extreme values. We also looked at doing a first derivative test for local extrema. That was where we looked at the signs of the first derivative on either side of the critical point, and that would tell us where the function was increasing and decreasing, and then we could draw some conclusions about our critical point. And then we looked at second derivative test, where we looked at the sign of the second derivative at our critical point. Second derivative would tell you about concavity, so determining whether the function is concave up or concave down helps you decide whether you have a local minimum at the bottom or a local maximum at the top. All right, so I'm going to do first derivative test for this one. It's actually possible on this one that you might do this problem several different ways, but for this one, the first derivative is pretty easy, and so I'm just going to use the first derivative test for local extrema to decide whether this critical point gives me a local maximum or a local minimum. So we'll go over here and look at that. All right, so I'm just making a number line. I'm putting my critical value on the number line, and I'm looking at the sign of that first derivative on either side of my critical point. All right, so when I plug in numbers that are less than 100/3 into my a prime, when I plug in values less than that are still in my feasible domain, I'll get a positive answer for my a prime. So my a prime will be positive. When I plug in values bigger than 100/3 but still in my feasible domain to my a prime, I will get a prime values that are negative. So that tells me that my a function left of 100 thirds is increasing and right of 100 thirds is decreasing. So that tells us that this is the location of a local maximum, a high point on the graph of my derivative. All right, which is what we were after. We were after the enclosed area being a maximum. So there's our test. We determined that our critical point gave us the location of a maximum. And then the last thing to do on any word problem is to make sure that you answer the question correctly. All right, so going back and looking carefully at what it asked us to find, it said what dimensions should be used so that the enclosed area is at a maximum. All right, so I have my y value here, 100 thirds, or if you want to rewrite that as a mixed number, 33 1/3. And our units here are in feet, so that's the y value. I also need to find the other dimension, x, here, or I could also describe that in terms of the 2x. So I'm going to go back in the problem to where I have an expression that relates my x and y. So x is going to be 50 minus 3/4 times the y value. That simplifies nicely. This all simplifies to be 25. 50 minus 25 is 25 feet. Okay, so there are dimensions, 33 1/3 feet. Sometimes I like to label my answers on the picture as well, and 25 feet in this dimension. All right, so there's the answer to the problem. We'll look at a couple of other optimization problems, same key steps in all of these. Main difference is in the function that you happen to be working with and what test that you might use to classify whether you have a maximum or a minimum value.